ಶೇರ್ ಮಾಡೋ ಆಪ್ಷನ್ ನೋಡ್ತೀರಾ?
ಶೇರ್ ಆಗಿದೆ, ಆಟೋಮೆಟಿಕ್ ಶೇರ್ ಆಗುತ್ತೆ ಬಿಡಿ ನಿಮ್ಮ ಬೋರ್ಡ್.
ಅಲ್ಲ, ನಾನು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ಆಪ್ಷನ್ ಕೊಟ್ಟಿದ್ದೀರಾ?
ಕೊಡ್ತೀನಿ.
ಕೊಟ್ಟಿರಿ ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಪ್ಷನ್.
ಸ್ಟ್ರೀಮ್ ಲೈನ್ ಮಾಡ್ತೀರಾ?
ಮಾಡಾಯ್ತು.
ಒಂದ್ ಸಮ ಹೇಳಿದ ಮೇಲೆ ಹೋಗೋದೇ ಇಲ್ಲ ಸರ್. ಒಬ್ಬೊಬ್ರು ಒಂದೊಂದು.
Can we start?
Yes, sir.
Okay. Now the next session is by one of our colleague, Mr. Asghar Pasha. He is working in Ramaya Engineering College itself. So he'll give the demonstration on numerical solution of coupled differential equations through Matlab. I request Mr. Pasha to proceed.
Yeah. Thanks, MVG sir. Dear participants, welcome to this session of day 5 of our FDP on computational methods in boundary layer theory. In this session, I'm going to discuss a few elementary things which are necessary to understand and program to solve coupled differential equations. So my plan of work for this session is like this. A quick review of ODE45, how it works for initial value problems. And then I'll teach you a technique to solve boundary value problem by converting it into initial value problems. And then Matlab program to solve second order linear boundary value problem. After this, I'll discuss solution to fourth order non-linear ODE, fourth order non-linear ODE, which is essential to understand. All these things are essential to understand the logic behind programming for solving coupled differential equations. This is in the first session. In the second session, after the discussion, we will do the programming to solve coupled differential equation. To start with, as you all are familiar with solving initial value problem using the ODE45 solver of Matlab. If a second order equation is given, d square y by dx square is equals to 2y cube, whose solution is y is equals to 1 by 1 plus x, with the initial conditions y of 0 is equals to 1 and y dash of 0 is equals to minus 1. What we do is we convert it into a system of first order ODEs like this. I call y as y1 so that I can easily program it. Y as y1, derivative of y dash, derivative of y is y dash, called as y2. Y double dash is dy2 by dx, derivative of this. I'm not calling it as y3 because in the second order, I'm stopping at the second order. I'm not calling it as y3. y1, y2, and its derivative dy2 by dx is 2y cube. Y I have denoted as y1, so it's y1 cube. I'm just rearranging it. I'm writing the first order, the conversion or the of the given second order equation. So the conditions y of 0 equal to 1 becomes y1 of 0 equal to 1. Y dash is y2 in our notation. So y2 of 0 is minus 1. So I'm storing y1 and y2 in my y, variable y. So the first column is y and the second column is y dash values. If you want to extract y dash values, you can extract the second column of y separately. Similarly, if you want only y, extract the first column of y, which is y1. So you have to create a function file. I'll do that. I'll share the screen and execute this program. I'm creating a function file. Any name you can give. For simplicity, I have given dy by dx equals to problem 1 x comma y. This y. Here, dy by dx has two components, dy1 by dx and dy2 by dx. Components of dy by dx. It is just the notation, dy dx1, dy dx2. You can write it in any way, a1, a2. Here, that capital A you can write. These are elements of that capital A, anything. It is simple to read, that's why I have written it as dy dx, dy dx1. Now, dy dx1 is b1 dy dx1 is y2. I have written y2 here. Next, dy2 by dx is 2y1 cube. I am writing that here. dy dx2 is 2y1 cube. Some matrix A, it is A1, A2, second element of A, first element of A. I'll create a function file like this and save it as PB1, problem 1. Next, I'll create a script file. I'll illustrate all these things. So in the script file, the boundary is from 0 to 1. X equal to 0 to 1 with the step length of 0.05 I have given. These are the initial conditions. Initial condition y of 0 is 1, y dash of 0 is -1. I have stored it as an array, inty, anything capital B, capital C, whatever you want. I have got the initial values of y. Now, this is the command, dear participants, to solve initial value problem. The command is OD45. You are calling that function. Calling that function. This is the independent variable. These are the initial conditions. The values will be stored here in the y. So y contains y and y1 and y2. y1 is y value, y2 is y dash values. It will be stored in y. What I want, it will be stored in y. y1, y2. I want y, solution y is required. So y is, this y1 is, suppress the row, first column of y. First column of y is y1. Second column of y is y2. You all are familiar with this notation. I want y, so I'm extracting that y, I'm plotting that graph, plot x comma y1. So this is y1 is the numerical solution. So I'm using the command here, hold on. So I'm saying hold on, in the same figure, I will write the exact solution. Exact solution is 1 divided by 1 plus x. But here x is what? Over the range 0 to 1 with the step length of 0.05. So element by element of operation you have to use. So it is not a normal division, it is dot. 1 dot division, 1 plus x you have to use. Plot x comma y exact in red color with plus symbol. So I am plotting it. Quickly we can see this. Just check whether I can share the screen. Okay, this is the function file. You have to go to new here, select new, new script file will come. So type function dy by dx problem 1, dy dx problem 1, x comma y. Here you are initializing y. Initially, I'm storing 0 values in y. That's why it's called as zeros. Dy by dx contains zeros. The size of dy by dx is same as size of y. So initially, I'm placing 0 values here. Next, first value dy by dx of 1 is y of 2. dy by dx of 2 is 2 into y of 1 the whole cube. End. You have to create a function file like this. Now, I'll go to main file. So in the main file, I'm using clear all to clear the memory, close all to close all figures, CLC to clear the screen. And these are X limits, 0 to 1 with a step length of 0.05 I have given. These are the initial values of Y, 1 minus 1. Now I'm calling the function, built-in function ODE45 at PV1. PV1 is the function file, X comma init Y. These are the initial conditions of Y. Y1 is the first column of Y. I'm plotting X comma Y1 and I'm saying hold on. I'm going to print the exact solution also. Exact solution is 1 divided by 1 plus X. It is element by element. So dot I have written plot that exact solution. So I'm plotting both numerical and the exact solution. And here for comparison purpose, I have written Y and YE. So this Y, the first Y contains 2 columns. The second YI is 1 column. Y contains Y and Y dash. That is Y1 and Y2. And Y is the exact value, Y value. So if this is done, I'll run this program to give the output. Fine, let me run this program. Okay. You can see the graph. This red colored one is the exact solution and the continuous one is the numerical solution that we have obtained. Let me analyze the output. So X 0 to 1 with a step length of 0.05. Y contains 2 columns. First column is Y1. Y1 is nothing but Y, the dependent variable Y. This is Y2. Y2 is Y dash values. Y1 and Y2. Next, I have printed Y, comma Y. If you have seen the last statement, it is YE. Y contains 2 columns. YE contains 1 column. It is only for the comparison purpose. You can see here 1, 1. Y exact value is matching with Y numerical value 0.9524, 0.9524, and so on. Okay, so this is a simple program. You know how to do these things. Now, same thing, using the numerical technique, how to solve programming. I'll program it. Instead of initial conditions, I'll give boundary conditions. And then I'll convert that boundary value problem to initial value problem. So you call that as a shooting method. Okay. Shooting method for non-linear differential equations. I have some non-linear differential equation of second order in the range A to B. Y of A given alpha, Y of B given beta. In the previous case, what we did was initial value problem when Y dash of A was given. Here I don't know Y dash of A, I know Y of B. Now I have to use a technique through which I have to convert it into initial value problem and then solve. So for initial value problem, we must know Y dash of A. I don't know, I'll assume it has some S, initial slope here. Y dash of A is equals to S. Okay. With that initial slope, I can solve that problem, initial value problem, easy because there's a program, ODE45 is there. It's simple, you have seen it. I can easily solve. With that initial approximation S, I'll get a solution, but that solution is not a solution of the given boundary value problem. So what I get is an initial value problem. I'll denote that solution as Y of X comma Sk. That is, I have obtained solution for the differential equation using or approximating the slope as Sk. Y of X comma Sk is the approximate or solution of the initial value problem with slope Sk, not the boundary value problem. And the solution of actual boundary value problem is Y of X. What we want is, we have to iterate it. We have to refine the value of S in such a way that the value of this initial value problem at B, this is a particular value here. Okay. This is at X equals to B. I am substituting. Y of X is the solution of the IDP. This is solution of IDP. I am substituting X as B, so I get the value of Y at B. That value of Y should match with the given boundary condition beta, that is Y of B. This is what I am looking for. This is what I am aiming for. Limit as k tending to infinity, Y of B comma Sk should be equal to Y of B, the boundary condition. So I'll draw the graph. This is the graph solution curve, but not the solution of the boundary value problem. This is solution of initial value problem with some initial guess S0 I have obtained. And this need not be equal to beta. If it is equal to beta, then this itself becomes solution of boundary value problem. That need not be equal to beta. This is a solution curve. So if Y of B is not that point, Y value, if it is not equal to beta, then we have to find another solution. Y of B comma S1 means I have to improve. I have started with S0. I have to improve it. I have to find S1, one more slope. such that y of b comma s minus beta becomes 0. The gap between this value, y value at b from the initial value problem should match with the boundary condition. So that difference should be 0. Now, how to improve this S1 value? Simple. I will use this is an equation. This is like f of x. This is what we are looking for. This is f of x equal to 0. F of x equal to 0. Start with s. F of s, function of s it is. It is dependent on s. Beta, b are all fixed. It is f of s. Start with s naught, use Newton-Raphson method and improve the value of s. So sk plus 1 is equals to sk minus, this is f of s, next this is f dash of s. Newton-Raphson formula, you know that sk plus 1 is equals to sk minus f of s by f dash of s. So f of s is this one. Solution of the initial value problem at x equal to b minus the boundary condition divided by its derivative. Beta is constant. This is dependent on s. So d by dx of y of b comma sa. What is the big deal here? Simple. Equation is simple. Newton-Raphson method is simple. What is the big deal here? I can easily get the solution. I can easily get the s values. I can improve the value of s easily. I can get the solution. What is the big deal? The big deal here is you don't know y of b sk explicitly. You know y of b s naught. One point you know. Y of b s1 you know. But you don't know the curve. You don't know this. The function is not known to you. We don't know the explicit form of y of b comma s. We only know the points on that solution curve. This one. For different slopes, S0, S1, S2, this curve will be different. So on that curve for a particular b value, I will be getting that y values. I only know that point, different curves. Right. That is a big deal. I don't know y of bs explicitly. So what we do is, as we don't know y of bs, I'll try to express the equation in terms of two variables. It was dependent on x earlier, but now s plays an important role. It depends on s also now. So the given equation, which was only in terms of x, now becomes y double dash of x of s, x comma s. Dependency on s. So earlier it was f of x comma y dash. When y was dependent on x, now it becomes x comma s. Y dash is also x comma s. And the condition. This is the initial condition given. Y of y of a was alpha, and y dash of a, I am assuming it as yes, some slope. So here I am rewriting this y dash of a as no, it not only depends on x, it is a function of s. Y dash of as is equals to s. I am writing here this prime. What I have written is derivative with respect to x. This is important with respect to x. So I have rewritten the given boundary value problem in this manner. I have converted it into initial value problem. Still not complete the process. I will differentiate that y double dash of x is. Y double dash of x I differentiate with respect to s. So dou by dou s, y double dash means function of x, y and y dash, three variables. Now use the chain rule. F depends on x first, x depends on s. Next, f depends on y depends on s, f depends on y dash depends on s. Okay, derivative of composite functions. I have used that concept here. Now, in our assumption, there is no dependency on x and s. X and s are independent variables. So this term is 0. No contribution from this term. X and s are independent. So this equation dou y double dash by dou s becomes dou f by dou y by dou s, dou f by dou y dash by dou s. Call it as equation number 1. This is an important step, this part. Now what happens in the initial conditions? The initial conditions are like this. Y at A is alpha, y dash at A is initial slope s. I will differentiate it. Y with respect to s I differentiate because it's dependent on s now. So dou by dou s of y, alpha is a constant, this is 0. And here y dash is s. Y dash is s, so its derivative with respect to s is 1. 0 and 1. Now I'll define a new variable. For that purpose, because that was not explicitly given, instead of getting one initial problem, I have to solve two initial problems, one extra. If it is there is one unknown, one extra. If there are two unknowns, two extra. Total 3 initial value problems. If there are 3 unknowns in the equation, S, T, and W something, I have to solve 3 extra initial value problems along with the given one. So 4 initial value problems I have to solve. Now, I am defining a new variable u of x comma s as dou by dou s of y of x comma s. Therefore, equation 1 becomes here. This equation dou y double dash by dou s, that becomes u double dash. First term dou f by dou y as it is. Dou y by dou s is u. I have denoted it as u. This part is u. This part is u dash. And this part is u double dash. I have defined a new variable u because there is a dependency of y on s. That derivative is u. So I have a corresponding u double dash equation. This is a counterpart of y double dash. Okay. Counterpart of y double dash is u double dash. On a similar line I have dou f by dou y, dou f by dou y dash, u dash, u double dash, like that terms will come. Okay. So this is an important step. I will be using this counterpart of y double dash double star. I will recollect it. I cannot show this slide again, so make a note of this. This is y double dash, u double dash, counterpart of y double dash. Now I am writing conditions on u. Obviously, you have seen that derivative is 0, means this is u. This is u. This part is u. U of a comma s is equals to 0, and this is u dash. U dash of a comma s is equals to 1. I have an initial value problem in u with condition on u like this. It's not t, it is s. U of a comma s is equal to 0 and u dash of a comma s is equals to 1. Okay, I have two initial value problems. Sk plus 1, I am improving the value of sk. Sk plus 1 is equals to sk minus, numerator is as it is, y of t sk minus beta, and the denominator is dou y by dou s, its derivative. This is Newton-Raphson method now. F of s by f dash of s. F dash, I am calling it as u. So this is the equation. We have to solve two initial value problems to get y and u. This is the logic. The working procedure I will explain. Working procedure. This is the given, okay, from the boundary value problem. This is for the boundary value problem. I am constructing initial value problem 1, IVP1. The same problem, same first condition, y of a equal to alpha, y dash of a is equal to xk. I am assuming it as sk. I have to improve this value. As there is one unknown, I will get one more set of initial value problem, u double dash, which is counterpart of y double dash. I have told you to remember this equation, double star. I am getting u double dash, counterpart of y double dash in this manner. Dou f by dou y into u plus dou f by dou y dash into u dash with the associated conditions like this. U of a comma s is equal to 0, u dash of a comma t is equals to 1. Okay. I will solve this equation because ultimately what is required is this number, numerator number. As a function, I don't know. Number I want. Y of b comma that for a particular value of s, I can find y using ODE 45. Denominator I was not knowing. So for denominator, I have constructed one initial value problem for which initial conditions I know. So I am going to get a definite value for u. This is not unknown. In the previous case, the initial condition is unknown, but here initial conditions are known. So I can find u. So this is known, this is known. I can get sk plus 1. Now improve sk plus 1 such that the boundary condition is satisfied. So what is the condition now? Step 3. So I will note the values of y of tsk as well as u of sbsk, and I will compute this sk plus 1. Step 3. I have to check the condition whether the solution of the initial value problem at x equal to b matches with the boundary conditions or not. If the difference is less than your tolerance limit, then stop the process. Otherwise, repeat the iteration. Okay. This is okay, but to write the program, you need to modify all these things properly. U and y dash things in one way, one numbering system you have to give. So I'll tell you how to do this. Working procedure. D square y by dx square is equals to 2y cube is the given differential equation, boundary value problem, non-linear, y cube term is there. Non-linear boundary value problem with condition y of 0 equal to 1, y of 1 is equal to 1 by 2. Actual solution is 1 by 1 plus x. Now I'll form IVP1. IVP1 is same equation, d square y by dx square is equals to 2y cube. Y of 0 equal to 1, same equation. Here I'll assume the initial slope, y dash of 0 is equal to s. So to use Newton-Raphson method, I have to define one more initial value problem IVP2. I'll write that. IVP2 is double star equation counterpart. Just recollect. Dou f, because f was a function of x, y, y dash, and x and t are independent, x and s are independent. So f depends on y, f depends on y dash only, the two terms in that chain rule part. So dou f by dou y into u plus dou f by dou y dash into u dash is u double dash. Now, dou f by dou y. Dou f by dou y. This is f. With respect to y, when I differentiate, it becomes 6y square. Dou f by dou y is 6y square into u plus, there is no y dash term on the right hand side, its derivative is 0. So u double dash is 6y square u plus 0. With the initial conditions, u of a equal to 0 and u dash of a equals to 1. Okay? Now, to write program, what I do is, I'll take y1 as y is y1. I have to differentiate till I get the equation. The equation is y double dash equal to something, till that. So y dash is dy by dx, call it as y2. Differentiate y2, we'll get y double dash. Y2 is the given equation. Y double dash is equals to 2y1 cube. Okay, where it is. The equation is like this. This is the differential equation. D square y by dx square is equals to 2y cube. So this part dy2 dx stands for y double dash. dy2 dx is y double dash. Y double dash is 2 into y cube. Y is y1, so it is 2y1 cube. I have to stop. I should not call this as y3. I have to stop at y double dash. If the given equation is fourth order derivative, then you have to stop at fourth derivative. Like that. Second derivative, stop here. Next, start the second second initial value problem. For that, the variable is u, call u as y3. Then its derivative u dash is dy3 by dx, call it as y4. U double dash, you have to stop. So I'm not calling it as y5, I have to stop here. U double dash equal to dy4 by dx, and that u double dash is this one, 6y1 square into y3. I'll tell you what it is. Yeah. This y1, y is y1, u is y3. I have started u from y3, right? So in terms of y, this u double dash, u is y3, and this is dy4 by dx. 6y1 square into u3. This is what I have written. So everything is in terms of y now. y1, y2, y3, y4, y5. y5 I have not defined. Its derivative is y5. I am not denoting dy4 by dx. Stop there. Now this is the actual conditions, transformed conditions to be frank. Y of 0 equal to 1. Y dash of 0 not given. I am assuming it as s. From this I have formed a new initial value problem. So initial conditions like this, u of 0 equal to 0, because in that there is no what? It was just a constant, its derivative with respect to s is 0. The second one had s in it, that's why it is 1. So it will be always like that, 0, 1 combination. Okay, 0, 1 only. U dash of 0 is 1. But now to write program, I have to write all these things in terms of y. I'm denoting y as y1. So y1 of 0 is 1. Y dash is y2. Y2 of 0 is s. U is y3. Y3 of 0 is 0. U dash is y4. Y4 of 0 is 1. Got it? So in the initial value problem which I discussed earlier, there were only two terms for y1, y2. Two derivatives part, dy1 by dx, dy2 by dx. But here there are only four terms, same extension. Construction you have to learn. You can extend the program in a similar way. And of course, one Newton-Raphson correction factor you have to add and check whether you are getting the exact result or not. That's important. So the problem is with checking the condition. How to check? How to check y of b sk minus y of b is less than tolerance? See, you are giving some OD for some step length here. Y b is the last value. You know b is 1, sir. What is the big deal? Y of 1, you can compute it. But no. As x varies like this 0, 0.05, 0.1, and so on. X equal to 1, this value, this index is different. I should know the length of x to know the corresponding y value, that is b value. To compute this value, I should know the length of x, number of elements of x. So I have to use length of y1. What is y1? Y1 is the first element, because in your y, you are storing y as y1, y2, y3, y4. This is your y. Y1 is y, y2 is y dash, y3 is y double dash, like that, or u dash, u double dash. So I want the length of y1. This is the concept to determine length of y1. I'll compute. Y1 is the first column of y, and I use length of y1 to compute the number of elements. And then, if I use this condition, the absolute value of y1 of n. So y1 is the first column of y. There are many columns. I am interested in the first column, and in the last entry is y1 of n. That last entry, which is the solution of the initial value problem, that should match with the boundary condition beta. If it does not match, means opposite. If it is greater than tolerance, if it does not match, you perform the operation. S mu is equal to S old minus that difference value divided by, this is what? This is U. Okay, you have seen the another initial value problem variable here, U. U is y3. This is the condition. In y, y1, y2, y3, y4, 4 elements will be there. Y corresponds to the actual y, y1, y2 is y dash, y3 is u, y4 is u dash. Correct? In the formula, that sk plus 1, our main aim was getting rid of this unknown function. Otherwise, the denominator you cannot compute. To get rid of that, I have formed a new initial value problem. So denominator becomes u. That u is y3 in this case. that u is y3. So everything, while writing program, everything should be in terms of that y, the elements of y. So that's why y of b is a is first column of y, and the denominator here u is third element of y, which is nothing but y3 of n. Third column, last element, y3 of n. So if you can program it, coupled differential equations you can easily solve. So what happens in coupled differential equations? There will be more unknowns. Conditions will be different. You may have to assume more slopes, S and T, and then more initial value problem comes, and you can program it easily. I'll illustrate those things in the second session. Now quickly let us do program for this. We shall do step by step.
Asha,
Yes,
what happened?
I'm sharing my Matlab screen now. 1 minute.
Okay, okay. Because dark screen it is there. That's
Yes, ma'am. Yes, ma'am. I'm sharing it. 1 minute.
it's okay.
Is it visible now, ma'am?
Yeah, it's visible. Program is here. Yes.
Okay, so I'll create a function file first. Function file. Okay, let me write that function file for you. You'll understand what it is. And then we can execute it. Function, you can call it as problem to dependent variable, independent variable, dependent variable. Next. Of course, function name you should give. You can call it as capital A, capital B, or whatever it will be. As it is derivative part, I'm just writing dy dx. Function name is problem 2. X comma y. So I'll initialize the values dy by dx. Initially, let it be all zeros. So zeros, but I should know the order or size of dy by dx. Size of dy by dx is same as size of y. Okay, I'm initializing dy by dx equal to 0. Now, there are 4 differential equations you can see here. First order differential equation, 4 equations and 4 conditions here. dy1, this is dy1 by dx. dy1 by dx is y2. dy2 by dx is 2y1 cube. dy3 by dx is y4. dy4 by dx is 6y1 square y3. I have 4 equations. To be frank, this is coupled differential equation. Okay. So I have to write those four equations here. Remember, y2, 2yn cube, y4, 6y1 square, y3. I'm writing it here. So the first element, the dv by dx is an array. Matrix actually, to be frank. Dv by dx1, first element is y2, y of 2. Next, dy by dx, dy2 by dx, you can see it is 2y1 cube. 2 into y1 means y of 1, the whole cube. Third differential equation, dy dx3 is equals to y of 4, fourth element of y. Dy dx4 is equals to 6 into y of 1, the whole cube. Y of 1, the whole cube into y of 3. Okay, so I'll write the function file like this. This is the function file. Let me do that. Okay, I'll take a new script file. So write that function file. Function dy dx is equals to problem 2 x comma y. Initialize the values. Dy by dx is equals to zeros. Size of y. Next, dy dx 1 is equals to y of 2. Dy dx of 2. Okay, see dy dx of 1, first element it is. Remember that. It's like a matrix, no array, it is array type. E of 1, E of 1 is y of 2. Dy by dx of 2 here is 2 into y of 1, the whole cube. Without this also you can write, safer side, let me write this. Y of 1, the whole cube. Dy dx of third element, third differential equation, it is y of 4. Dy dx of 4 is equals to 6 into y of 1, the whole cube, into y of 3. End. So you have to save this as PB2. Anything, but it will automatically get saved as PB2. Control S. Yeah, see automatically file name is PB2 here. Save as PB2. Next, now open one more file, new script file. Now let us write the program similar to what we wrote earlier here, with an extension of Newton-Raphson scheme we have to write, correction scheme we have to write. So it's always better, whatever you're writing, if you write the comments, it's always better. So comments can be written after this percentage symbol. So what you are doing is you are creating a script file to solve second order non-linear equation d2y by dx square is equals to 2 into y cube, 2y cube, under the conditions y of 0 is equals to 1 and y of 1 is equals to 0.5. Clear all, clear the memory. If you want, you can close all figures, clear the screen, and tolerance you can set. I have to check now the difference between the value of initial value problem at B and the actual boundary condition. So for that, you have to set a tolerance. So you can say 10 to the power of -6 or -8, whatever tolerance level you want, you can set. Next, YA is equals to 1. This is the initial condition. You can take this as input from the user, but you know that I'm calling it as YA. Y of A is YA, which is 1. Next, YB is the boundary condition. YB, this is 0.5. Next, S old value. S old means here the S value. Okay, take S value from the user. Take S value from the user. So S is equals to, or I call it as S old because I have to iterate. I'll call it as S old is equals to input. So I'll take this from the user, new line, enter the initial guess S naught for y prime. This is for the y dash, colon, some space, and close it. So this command will wait for your input S old. S new, you initialize it. You can initialize it to any value. Initialize it as 0. Now I need these dummy variables. I'll tell you why. Take it as 0 and k equal to 1. I'll let you know what k and I are. I'll perform this iteration while k is less than some 40 iteration. So I'm saying perform maximum 40 iteration and do it. While k is less than 40, I have to solve the ODE. What is it? XY is equals to, you know the operator ODE 45 at the name PB2, it is at PB2 comma, you can write the conditions here. Zero, 1, y of, what is it? The x limits, these are x limits, x starting value 0, ending value 1. So I'm not initializing the ODE45 itself will take the appropriate step length and it will compute. So I'm just giving the X range. X range is from 0 to 1. And now you have to give the conditions. If you remember, the conditions are what? Conditions are here. One S01. These are the conditions. One S01. Give these conditions in that order. One S01. One semicolon S. S is S old here. The value that you have taken as input from the user. S old 0 1 S old semicolon 0 semicolon 1. Close this. So simple command to solve initial value problem. You have stored the function file as pb2 x range 0 to 1. I have not given the step length. Let it automatically compute it. And these are the conditions. 1 S old 0 1. This needs to be improved. Now, for simplicity, I'll write y1. I'll extract. I can directly use y colon comma 1. But calling it as y1 is simple for cross-checking the conditions, verifying the conditions. Y2, y1 are simple than calling it as y of colon comma 1. So it's better you store the columns of y in y1, y2, y3 and y4. And you know what all these things. Y3 is y of colon comma 3. Y4 is equals to y of colon comma 4. So y1 is y, y2 is y dash, y3 is u, y4 is u dash. Now to check the condition, I need length of y1. I'll call it as n. N is equals to length of y1. So if I have not defined this, I should have written it as here y of colon comma 1. So y1 is simple here. Next, check the condition. If absolute value of y1 of n, last value, y1 of n minus the boundary condition. Boundary condition is yb 0.5. Yb is less than tolerance. Okay, if I say less than tolerance, it means that the selected S value is correct and whatever I am getting now, it satisfies the conditions. So I can print the solution. So f print f. If it is satisfying, you print what? Print f numerical solution. Numerical solution of the given differential equation after percentage d iterations. After percentage d iterations is colon space, so comma k. So here k I said initially 1. So when In the first iteration itself, it gets satisfied. You are printing that k value. K equal to 1 means in one iteration itself, I got the exact answer. Okay. After this, what I do, I'll print the values required. I want x. I want y1. I'll print x comma y1. Then I said it was dummy variable, I equal to 0. Now I'll make I is equals to 1. And I'll check if I equals to 1 means I have obtained a solution. If the solution is not obtained, if this condition is not satisfied, I remains as 0 means I have to perform this iteration. So this dummy variable will help me to get out of the loop and close the program. Okay. So I'm changing the dummy variable. Whenever this gets executed, I becomes 1. You can break the loop. Now I'll plot it. Plot x comma y1. I will plot. This is the numerical solution. If you want, you can label it. So I'll not go in detail related to the plotting options that you can explore on your own. X label X, Y label Y, grid on, and the title and other things you can give. So I'll just focus on the programming aspect. I'm plotting the numerical solution, what I have obtained. And I'm saying hold on, means wait. In the same figure, I will plot the numerical solution as well. So numerical solution is 1 by 1 plus x. So it is element by element operation. That's why you have to use dot here. Okay. But as you have seen, I have not defined x, right? 0, 1. The range of x is not defined. This ODE 45 itself will take care of that. It will take care arbitrarily step lengths and then it will improve. I'll show you when you get the solution. So there is some x range here. You don't know what it is right now. That's why I have used length to compute the last element. So y is equals to 1 by 1 plus x. This is the exact solution. Now I will plot this exact solution. Plot x comma exact solution. I'll plot it in red color with plus symbol. And then return. Return. Okay, so when this condition is satisfied, all these things will come and it will return. It will break this loop. If this condition is not satisfied, it will come out here. Else part now. Else part. Else what I have to do? I have to improve the value of s. How? S new is equals to s old minus y1 of n, y1 of n minus yb, y1 of n minus yb divided by u. U is y3, u of b it is. So y3 of the last element, y3 of n. S old minus f of x by f dash of x type. So I'll do this and I'll print this iteration value. At this iteration, what I'm getting, I'll print it. Iteration number I'll print. Percentage D here, iteration number 1, 2 like that. Slash T, I'll give some space. Slope equals to percentage F for floating character number, slash T, I will write y of 1, what y of 1 is. This y of 1, whether it is equal to the boundary condition 0.5 or not, I have to check. So I'm checking it in this output itself. I'll come to know. So K is iteration. S new is the new slope you are getting, and then y1 of n is the boundary value of y at the end point associated with the initial value problem. So I'll print this and I'll end. Okay. So if this condition is satisfied, it goes inside, I becomes 1 and it will come out of this loop. Otherwise, else, this condition is satisfied. Next cursor, after this cursor will come here, program continues. What you have to do, S old is now S new, because it will go and sit in S old place, the new S value that you have computed. S old is S new. I'm increasing the iterations. So K becomes K plus 1, the K plus 1 value. Till 40 iterations I'm doing. Earlier K was 1. After first stage, this becomes 2 and so on. End. So this while loop is clear now. Even after 40 iterations, if it does not converge, if this condition is not satisfied, the dummy variable I what you took as 0 will remain as 0. It will not get converted as to 1. It will remain as 0. So now you have to check. If I is equal to 0, you can conclude that method does not converge. If I equals to 0, there is no need to check I equal to 1. If I becomes 1, the entire, it will come out of the program itself. Return statement I have used. If I is equal to 0, f printf now think whether I equal to 0 part is required or not. Can we directly print this? Method does not converge in %d iterations. But while coming here, I have given one increment to k. So k value is 1 more than the actual number of iterations. So k minus 1 you have to type here. So print this, and also you can say try with new approximation if you want. End the entire program. That's it. Now save this before executing. I will call it as main program for problem 2. Save. Let us execute this. Okay. There is an error here. Column line 32. Okay, I have to start with this. Okay. Fine. Okay, you know that y dash, actual problem is y is equals to 1 by 1 plus x. So y dash is minus 1 by 1 plus x the whole square. So y dash of 0 is actually minus 1 it is. It is minus 1. We can give other value. We don't know. No, I know the solution. I have written minus 1. See, I got the solution to this non-linear differential equation. You can see the difference between exact and the numerical value. No difference. What I'm printing here, I'm printing x and y as I said earlier. See the step length it has taken. The other digits are not visible. It will check. When the method gets confidence, arbitrarily the step length changes. This is ODE 45 method. So you got the solution here. Now I got the solution in only one iteration because the difference is less. I have substituted minus 1. The slope I know, but in the research problem, what you know, you won't be knowing what the slope is. So in that case, you have to guess. You have to trial and error method. See, I'll give minus 0.5. It has converged. It has converged in how many steps? In 7 step itself, it got converged. I gave minus 0.5, the actual slope minus 1, and then solution. Give minus 2 away from the actual one. Still, it got converged in 7 iterations. So it all depends on the differential equation also. Some differential equations will be very, very sensitive. So the initial guess, you have to select properly. Minus 3 if I take, see it is not converging. Method does not converge in 39 iterations. Okay, maybe I missed one k here. So fine, we just write k there. Method does not converge in 39 iterations. No, it's not coming for minus 3. Minus, okay, plus 1 if I take, what happens? Let us check. Again, not converging. 0. It converged. In how many iterations? It got converged in 9 iterations. Actual slope minus 1. Okay, so this is solution of nonlinear differential equation, which gets converted to coupled. Actually, all 4 equations what you have are coupled differential equations. In the next session, after the break, I will solve 4th order differential equation, and then directly one coupled differential equation I'll take and I'll demonstrate it. So let us break for 15 minutes. We shall meet again at 3:50. Thank you.